So our next speaker is Arantxa, and she will present a roadmap for lookup tables. Please welcome Arantxa.
Thanks a lot. OK, so I'm sorry if some of you are here because you thought this talk was going to be advanced. Apparently, it has been tagged like that, but it's not an advanced talk at all. It's more like personal opinions on lookup tables. So I have been working on lookup tables for like a year and a half now. And I feel like I'm a bit trapped into this dichotomy between what I think it would be cool to do and what makes sense, actually, to do in an application level. So let's start from the beginning. What is a lookup table? A lookup table is a scheme where a prover wants to convince a verifier about the fact that we have two sets, a potentially huge one. You can think of it as a table, as a vector. And then we have a smaller one that we want to prove that only has elements that come from the former. One important thing is that lookup tables are usually not protocols by their own. It's not something that we want to do and stop there. They're usually, most of the times, sub-protocols. So it is important that when we extract the information from the huge table and we get it in a tiny set, we are still able to manage this set. We want this set to be something still meaningful, because we will keep doing computations on that. And for instance, like a graphical example, we have a big set, size big N. And there are some of these elements that we want to use for something else. So we will extract them. They may be in any order, sometimes also repeated. And we end up with a set that is potentially way smaller, of size small n. And now we want to make computations on this small set and forget about all the information that we don't need anymore. And I have classified a bit lookup tables depending on the application we are using. And I will say we have two kinds of tables. We have static tables and dynamic tables. So the table is this big thing that we start working with. For a static table, the case is that the table doesn't change. It's always the same. And, well, it may change a bit, but we will see that later. Application of this, for instance, are range proofs. The table just has all the elements within a range, and we want to prove that our smaller set has only elements that fall in the range. Membership proofs, here is where, well, static tables are not ideal, but we have a set of public keys of some users that are authorized to do some computation. And we want to link, for instance, ourselves with that set. And then also memory access, which also changes depending on the application. But we have this, like our memory, and we want to access maybe a chunk of it. And then we have dynamic tables. Dynamic tables are tables that are built on the fly, I would say, during a computation. And they are getting very, very much into the stage now because of the zero-knowledge Ethereum virtual machine. And they are usually used for input-output relations. So for instance, when we want to prove that something is the output of a hash, the arithmetization of the hash is very expensive, also for bitwise operations. So sometimes it's just better to prove that our input-output pair is inside a pre-computed table. And then we have the lookup itself. The lookup is the relation that links the smaller vector with the big table. And then I have decided we can have these three scenarios. I have divided the constructions we have so far. And it may be the case that we want to hide this relation. For instance, if we are using range proofs for snarks, our witness is secret. We want to keep it secret. So we don't want to link which are the elements, for instance, within the range that we are using for our witness. In membership proofs, it's the same. If I want to extract my public key from a huge set and I want to stay anonymous, of course, I don't want to leak this relation. And also, in a similar way, for anonymous credentials. Then it can be the case that the lookup table is part of a computation that is public and fixed. And in that case, the scenario I can think of is memory access. I know which is the part of the memory that I will have to access at a specific step of a computation. And that's fixed from before. And then the last case I can think of is when we do lookups on the fly. This means that it's not fixed from before. It's not something that I knew in advance. But it's also not something that I want to keep secret. I'm OK with letting you know which is the lookup that I'm performing. And you can think this for range proofs when the witness is not something thicker. And input-output relations. When I do a table on the fly, when I have a dynamic table, and I compute something on it, it may be the case that I'm not interested on hiding it. And then we have something that we always want. In all these scenarios, there has been a hype into taking care of the prover. Apparently now we do care about them. And there are several things we would like a prover to have. First of all, we want our prover to work with small degree polynomials. If you are not very familiarized with the univariate setting, pairing-based proving systems, you can just skip this part. But the idea is that if we have a huge table, we will commit to the table as a polynomial that will have huge degree. But when we make it to work with a smaller set, we don't want that set to be committed to, with a polynomial of degree, the big table. Why? Because prover computation will always depend on the degree of the polynomials the prover is manipulating. So we want to keep that thing as small as possible. Ideally, each vector will be committed using a polynomial that has degree the size of the vector, or the size of the set. And then, a bit more advanced, if we construct these polynomials using Lagrange bases, which is what we usually do, we want these bases to correspond to set of roots of unity. Why? Because we can do FFTs on roots of unity. We have sparse Lagrange polynomials. We have sparse vanishing polynomials. Everything becomes cheaper and nicer. Then, and this is, I will say, the most important thing, we want a prover that is table independent. So if I'm only going to use 4 elements out of a huge set, then I don't want my prover to depend on the huge set. I want my prover to depend on the 4 elements that I need. So I want to break this link. Then, once we are table independent, we only depend on the small lookup, on m, small m. And if we are going to depend on small m, hopefully we will depend linearly on small m. We don't want something quadratic, cubic, or anything like that, so as cheap as possible. And in an ideal world, why not? We also want a prover that is linear on the size of the lookup in the field. And this is a lot. This is not trivial at all. So pursuing this ideal prover is that we have started working last year. So all these works have been published after May 2022. And this first work, which is Caulk and is a work I co-author, is the first one where we say, OK, what happens with the prover? Let's take care about on the prover. But before that, we had 2 other constructions on Lookup that are Lookup and Halo 2. And after that, I really want to give credit to this great work by Alin Tomescu and others. So let's see what happens. In Halo 2 and Lookup are both lookup tables, schemes for lookup tables, that are built mostly for the case of snarks. And they do apply a lot of techniques of sorting, permutation, copy constraints, and achieve a prover that is linear on the table. Still, I want to highlight that even though they were not constructed for this setting, in my classification of lookups, they are what I would call dynamic lookups. So it's linear on the table, but for dynamic lookups, and we will go to this later, is probably the best we can get. But they were not built in that setting. And then both constructions can achieve zero knowledge. Again, they were like built to work for snarks. And then in 2020 appears this work aggregatable subvector commitments for stable cryptocurrencies that heavily used some techniques by Feist and Kovacevic. This work was just published this year, but there was a blog post before. That is the one this work relies on. And this is not for lookups. This is not a lookup work. It's for subvectors. The difference is that in a lookup, we can think of a lookup as a generalization of a subvector. We are taking all the elements from the previous vector, but in any order, and we want to allow repetitions. So a subvector just extracts a bit of the vector in the same order, no repetitions, and we want a bit more. But one thing that they do, and I think it was a breakthrough for everything that came after, is realize that if we have a static lookup table, we can pre-process stuff. If the table is not going to change in the entire protocol, it pays off to make some expensive computation before, and then we can have a very efficient prover. So with this pre-processing and the fact that they work with small degree polynomials, they achieve a table-independent prover. So this is what the prover in Zcon4 looks like. It works with small degree polynomials, so that's good. It doesn't work over roots of unity, so it's not very efficient, but it is table independent. So for opening a subvector of size m, the prover does work that is linear on m. But it's not a lookup. It's a subvector, so we are not there yet. And well, back then we didn't even care about the prover in the field, I think. So that's far. And then in May last year, we published Caulk. We built on the top of Zcon4, and then Caulk Plus came with a very nice improvement on Caulk. These two works fall in the following setting. We assume static tables, but Caulk was thought to work for membership proofs or for range proofs for snarks, so we asked for zero knowledge. We were aiming for zero knowledge. So starting from Zcon4, we managed to get something meaningful, to get a polynomial that is committed to in roots of unity. This implies that we can easily plug the output of our lookup into a new scheme. We can easily relate it, because mainly we build schemes for vectors that are committed using roots of unity. But that was at the end. In the middle, we have something with a very awful basis that gets expensive, but almost there. The way we achieve this is basically build a protocol that relates weird bases with bases corresponding to roots of unity. Then we made it at Lookup. It was a subvector commitment. We add this, we allow for permutation, for repetitions and change of order, but it was not linear. We made it quadratic on the size of the lookup. How? Well, by making what we call the lookup argument itself, which relates a vector with another vector that has the same elements in any order and with repetitions. So this is really different from the techniques that were used before in Halo 2 and Flookup. And then we were not aiming for a prover that was linear in the field, not because we didn't want to, we were not even linear in the group, but we added zero knowledge. The problem is that when we added zero knowledge, we made it table dependent. Logarithmically, but it was table dependent. So it was just a sub-protocol to prove that some vanishing polynomial corresponds to a set of roots of unity. And then this was a situation for Caulk. It was, at that point, good enough, but there was a lot of room for improvement, as you can see. And just, I think, a month and a half after, appears Caulk Plus that gets rid of the dependency on the table for the zero knowledge argument. When I say the same, I mean a protocol that does the same. Techniques are very different. And they really make the most of the pre-processing here. And we are back to a table-independent prover. So we still have room for improvement in the sense of using only roots of unity and having a linear lookup. In the middle, there was another work that is called Flookup. I'm not mentioning it because of time constraints, but also it falls in a very different setting. I will be happy to explain it to anyone. And then Baloo and CQ appear, and suddenly we change the setting. We are here now. We have a static table, but we don't care about zero knowledge anymore. Now we care about these lookups on the fly. And this is because we start looking for lookup tables that can be used in something like the zero knowledge Ethereum virtual machine. So mostly for input-output relations. And well, we don't consider zero knowledge, neither in Baloo, neither do the authors of CQ. And Baloo does build in top of Caulk Plus. We made the lookup linear. And the idea is that we see a lookup as a matrix vector product, and then we can apply snark techniques. Our prover becomes linear in the group, but we still have this problem with the roots of unity, and our prover being definitely not linear in the field. CQ comes with different techniques, so it doesn't build on top of any of this previous work. It does build in top of a work by Havoc, also late last year, and they make it to work only with polynomials that are committed to using roots of unity. How? Well, they use logarithmic derivatives. This was the thing that Havoc brought up in his work, multilinear lookups, and a lot of pre-processing. It's a very smart way of making the most of the fact that the table is static. So here is where we are since December in terms of univariate lookups. And now I would like to ask some questions. I mean, this is where we are, and I have a lot of ideas of things that maybe we can do. I am very open to discuss whether they make sense or not in terms of application. So my first question is like, can we have everything? Can we have a prover that is linear in the field without sacrificing the verifier? Because in the multivariate setting, we can have all of these. But there is a bit of change in the verifier computation time. I'm also open to discuss whether we should just sacrifice the verifier and give up. But let's say in the univariate setting, still, I think it's a very interesting question, whether we can maybe use a bit more of pre-computation, like squeeze it a bit more, and try to get a prover that is linear in the field. Then both Baloo and CQ fall in this setting. My question is like, can we do it zero knowledge? Like, if we want to use them for things such as range proofs for snarks, can we just make them zero knowledge? My guess is yes, and I'm pretty sure about this. Haven't done it. If any of you want to do it, I will be happy to discuss that. And then, can we do the third setting, the public and fix? Or even more, does it make sense? Because in this setting, I think we can aim for an even more efficient prover, because if we have a lookup that is public and fixed, maybe we can also do some pre-computation on that, not only on the table. But the question is like, for which setting? My guess is yes, you can do it. Both Baloo and CQ can be adapted to be for like fixed lookups. And the only thing is that CQ doesn't distinguish order permutations in the lookup. So if you extract two sets that have the same elements, same repetitions in different order, you cannot distinguish them. But I still think that may not be necessary. And then another question I have been asking myself, this is like back middle last year, is like, what happens if our static table just changes a bit? Like in membership proofs, which makes sense, right? I have a set of 1,000 authorized members, and I may want like to update some of them. And what I'm asking is like, can we have maintainable memberships? Because when we pre-process this table, and then we update the table, we change some elements in the table, we have to update all the pre-processing. And this is possible in all the constructions, but it's not efficient. So maintainability is like efficient updatability. And in the case of membership, my guess is yes, we can do this. We can mix Caulk Plus, and this is a very nice result we have from AsiaCrypt last year. And I have been thinking on doing this for a long time. I just gave up. You're welcome to try it. And then I am clueless about maintainable lookups yet, but I also try to think in which setting will it make sense to have a maintainable lookup. Like, not in range proofs, of course. You are not changing the, updating like pieces of the range. And then another question that I have is like, what happens with dynamic tables? It's like, we forgot a bit about them, but this is actually what we should pursue a bit for applications such as the Ethereum virtual machine. And are there any of the techniques that we develop later useful to make, for instance, Flookup or Halo 2 more efficient? Can we just like see what happens with the schemes that we left? And then, of course, there is a question on folding. So this is the hype now, and my question would be like, for instance, there are many, but one is like, are these univariate lookups folding friendly? Can we plug them into something like Nova? Does it make sense? Shall we just stick to like multilinear lookups that we have been proved already they are folding friendly? And last but not least, I think that in both cases, in Baloo and in CQ, this fact that the table is on the fly is just because it's not fixed. It's not zero knowledge. We don't want to hide it. But at the end, what we are doing is like computing something and then convincing the verifier that I have computed something of some form. I have computed a lookup. I'm not saying which is a lookup. I'm not hiding it. And my question is like, I think this was a bit accidental and somewhat, but can we have that for other relations? Like, what happens if I can do a linear combination on the fly and then say, hey, this vector is a linear combination of these other vectors? That's it. It's not fixed. I'm not hiding it. Does it make sense to have something like this? I think this is very interesting, and I would really like to listen about applications that this can have. And yeah, I think I went a bit fast, but that's all.
There are no questions in the Hova app, but if anyone in the audience has a question, I can bring the mic to you. Oh, okay, thank you. So the first question is, do you have more details on having no zero knowledge but dynamic table?
What do you mean? It's your question?
Yeah, someone posted on Google. They asked if it's possible for it to have no zero knowledge but dynamic.
Yeah, actually, there is something. For instance, Flookup, the description of Flookup is without zero knowledge. It's a dynamic table without zero knowledge. You can add zero knowledge. Same with Halo 2. If you go to the book, first you have the description without the zero knowledge, and then it's added. So yeah, I would say zero knowledge when we can, like I mentioned zero knowledge, like we can achieve zero knowledge, but also we can just stick to the succinct proof.
The second question is side channel resistance something that needs to be considered?
Side channel resistance?
Yes.
I am a bit clueless about what this question is about. I don't understand it.
Sorry, I'm not super familiar with the subject, but I was wondering, like in some other areas of cryptography, if in the input is secret, like a key, you need to make sure that the computation doesn't, the timing, characteristics of, looking up doesn't leak any information about the key. So I have no idea if this is something that needs to be considered in this context, so I'm just wondering.
Let me think. I mean, the key can be, what you're saying is that you're hiding the key, and we want to perform lookups without revealing it.
Yeah.
Okay. Yeah, that's the case, for instance, in membership proofs. You have public keys, but you want to keep it secret when you extract it because it can be linked to you. So the table is secret, but the thing is not. And in the case of snarks, for instance, it's the opposite. You want the lookup table to be hiding at every moment. So this could be, in a snark, the witness can be a private key, and you want to keep it secret for the entire computation.
Right.
So yeah, if I understood the question, yes. Mary wants to say something?
Any other questions? Yeah, I saw this first.
So I was wondering a bit about post-quantum security. So a lot of those techniques depend on KCG commitments. So what are the best candidates? Which of those kind of goals? How much back are we thrown if we want post-quantum security? What's the best schemes there?
For which of these achieve post-quantum?
Yeah.
None of
them. Maybe Flookup if you use IPA. Or
you can.
To be at the start again.
The thing is that from the beginning, Lookup, you can probably compile it with a different scheme. But for all the other schemes, we heavily rely on the fact that we can pre-process individual KCG openings. So I don't think we can make any of them post-quantum. They are not. They are very much compiling strict. It's like KCG.
This is more a comment to the previous side channel question. My understanding is that most of the time applications of zero-knowledge proofs are done in a setting which isn't necessarily side channel resistant at all. You're trusting your hardware. You're trusting that your hardware is OK for this kind of thing. The one exception that I'm aware of, there's probably more exceptions, is something called zero-knowledge proofs as a service. And that's really sort of saying you have multiple provers that you're outsourcing your witness to, you sort of secret share it, and then if any one of those components is okay, then in that situation you can be sure that your witness isn't leaked. But this is probably an area where we need much more active both research and engineering, because we're probably quite far behind signature schemes for this sort of thing.
There's another question.
In any of this situation, if we assume the verifier can have access to the table or part of it, is there a...
To the public, to the big table?
Or to the M thing?
To the lookup, for instance, in the case of the work by Thomas et al., which is a subvector that you can think of as a particular case of lookups, the verifier knows exactly what the prover is going to open. And in the other cases, it depends on the application, but generally, we don't want the verifier to have access on the clear. The verifier usually receives a commitment to this lookup, and that's always communicated in a succinct way. Whether we hide it, we made the effort to hide it or not, that depends on the application. But on the clear, it could be, I cannot actually think of any nice application. Just, subvector openings, vector openings, but that's way simpler.
But if we do it, could we get a speed up?
Sorry?
Could we get some speed up? That the verifier knows the membership, it doesn't, I guess.
Yeah, no, I cannot think of one. like, I can think of applications again where it's okay if information is leaked.
But there's no
But
proof.
like to have it on the clear.
Any other questions? There's one more question in the Hova app. And the question is, what makes dynamic lookup difficult?
So the thing with dynamic lookups is that I'm pretty sure you cannot get better than linear on the size of the table because you cannot use preprocessing. So preprocessing, it's like you have some work by the prover that is made in advance, but the work is still there. So if you don't have the chance to do preprocessing, the work has to be done by someone, and that person is the prover, and I cannot imagine a way that we can get better than linear. I'm pretty sure, I don't want to claim big stuff, but we cannot get better than linear. So it's not that it's difficult, it's that there is no much room for improvement there. As you can see, like in all these works, we really squeeze the possibility to pre-process stuff, and with a dynamic lookup, we lose that. Maybe we can make a bit better in concrete efficiency the previous works, but I don't think we can do anything asymptotically.
Okay, thank you for the discussion, and thank you, Arantxa.
Thanks.